Okay, this is the diffuser example. I'm going to start off by reading the problem statement. We have air at 10 degrees Celsius and 80 kilopascal enters the diffuser of a jet engine steadily with a velocity of 200 meters per second. The inlet area is 0.4 meters squared, and air leaves with a very small velocity. We want to determine the mass flow rate of air through the diffuser and also the temperature of the air at the outlet. Alright, so here we'll go ahead and set up the problem. This is the first problem that we're looking at where we're using both the mass balance and the energy balance, and we're looking at one of those 5 important devices that I talked about for the exam too. In this case, we're talking about a diffuser. So the very first thing we always want to think about is what is the purpose of the device. So the purpose of the device for a diffuser, it decreases the velocity and it increases the pressure. So we want to keep that in mind as we solve this problem. Okay, first thing, let's go ahead and define the system. In this case, our substance is air, and our device is a diffuser. So we have air in the diffuser, that's our system. And classifying the system, air is something that we model as an idle gas. And a diffuser is one of the examples of an open system. So that defines the system. For our sketch, okay, the sketch, remember in the sketch for chapter 4, all we're really wanting to do is kind of do a rough engineering sketch. So we can just sketch the general shape of a diffuser. It has a small inlet area and a large outlet area. And then we can put some of the known values that we have. Here we have the inlet and the exit. So the exit we call 2. The inlet we call number 1. At the inlet, we can go ahead and put all the properties that we're given at the inlet. We're given temperature, pressure, and velocity and area. So we have here at the inlet, we know T1, we know P1, we know velocity V1, and we know area A1. At the exit, we know something about the velocity, that the velocity is very small. So at the exit, we'll go ahead and put for now just V2. So this would be our sketch. Don't have to worry about any properties sketches for chapter 4. Just want to do like an engineering sketch. Something like this will be perfect. Next thing we do is apply any conditions. So the first type of conditions we apply are the chapter specific conditions. And all of these devices that we're studying in chapter 4 are steady flow devices. This problem even says that it's a steady flow. So we want to mark that it has a steady flow. So that's one of the main conditions. That's the chapter specific. And then the problem specific conditions apply to what type of device we have. So here we have a diffuser. So we'll flip back into our notes where we were talking about diffusers, and we can make the same assumptions that we made whenever I was giving you the general conditions for a diffuser. So if you look back in your notes for a diffuser, we assume that the change in potential energy is negligible. Also, we assume that there's no heat transfer unless the problem states it. So this problem doesn't say anything about heat transfer, therefore we can neglect the heat transfer as well. And then also both a nozzle and diffuser require no work input and produce no work output. So these 3 things are things that we can cancel out in the first law, and those become our problem specific conditions. Last thing we need to do is go ahead and list out the properties. So the properties, we identified 4 properties at the inlet. Let's go ahead and give those values. For T1, that was 10 degrees Celsius, or in Kelvin, it's 283 Kelvin. For the next thing is the pressure at the inlet, 80 kilopascal. Next is the velocity at the inlet is 200 meters per second. Then we have the inlet area is 0.4 meters squared. Next, we see that air leaves with a very small velocity. So thinking about what does that actually tell us? It doesn't necessarily mean that the velocity of the air at the exit is 0. That would be impossible, otherwise the air would not be able to physically move out of the diffuser. So it's not saying that the velocity of the air at the exit is 0, but the velocity is very small. And so if we look at the kinetic energy of the fluid at the exit, the kinetic energy is proportional to velocity squared. So if we take a very small v2 and then square it, we get an even smaller number. So we can say that instead of velocity v2 being 0, we can say more accurately that the kinetic energy at the exit is roughly 0, or just a very small number that is negligible. Now we're ready to go ahead and solve the problem. So we're looking for a couple things. It wants us to find the mass flow rate and also the temperature at the outlet. So we're looking for the mass flow rate and the temperature at the outlet, that's T2. Alright, so what we want to do with all these chapter 4 problems is we want to apply our two main equations and see what those two equations tell us about the system. So our main equations from chapter 4, that's the mass balance and the energy balance. So the first thing we can do is apply the mass balance equation for a diffuser. So for a mass balance, our diffuser has one inlet and one exit, therefore it's a single stream system. So we start off with a single stream mass balance equation. m dot 1 is equal to m dot 2, or in other words, we have a constant rate of mass flow through the device. So if we're actually looking for the mass flow rate, what this equation tells us is the mass flow rate we can calculate either at the inlet or at the exit, and that is the mass flow rate through the device. So we can calculate either the mass flow rate at the inlet, be equal to V1 A1 divided by specific volume 1, or we could do this at the exit. So just using the mass flow rate equation along with the mass balance, we can see that by looking at these two equations, we know almost all of this information right here. We're given the velocity at the inlet, we're given the area at the inlet. All we need to calculate is specific volume of the air at the inlet, and that will give us the mass flow rate. So how do we calculate specific volume at the inlet? Think about it for a second. So this substance that we're dealing with actually is an idle gas. So for all of the idle gas, the way that we get property values like specific volume is we use the idle gas law. So if we look at inlet number 1, at inlet number 1 we know properties. Here we know the temperature and we know the pressure. Those are our intensive properties at the inlet. So if we write the idle gas law at the inlet, P1 V1 is equal to R T1. We can solve for the specific volume at the inlet. It's just R times T divided by P. And then for R, we want to use the R for air. So R for air should be equal to the universal gas constant divided by the molar mass of air. Alright, so let's take all of this information. Let's take the R for air, and let's also take this equation for specific volume 1. We're going to substitute both of those things back into the mass flow rate equation right here. So what we end up with for mass flow rate, we get velocity 1 times area 1, and then divided by specific volume 1. So specific volume 1, we have R times T1 over P1. So R and T1 on the bottom, Here P1 goes back up to the top. But then our R for air is equal to universal gas constant divided by molar mass of air. So we can also write this as V1 A1 P1 divided by R. We have the universal gas constant, and then molar mass of air goes back up to the top, and T1 is on the bottom. So now we're ready to go ahead and just make sure that we look up all these property values correctly. We know V1, A1, P1, T1. We just need to look up the molar mass of air. Universal gas constant, we know that is just 8.314 kilojoule per kilogram times Kelvin. That's in SI units. So let's go to the tables now and we're ready to calculate the mass flow rate. So pulling up our tables, what we're looking for is the molar mass of air. So here's table A1. For air, we have molar mass of 28.97. And that's in kilograms per kilomole, I think is what that said. Yeah, kilograms per kilomole. Alright, so we have a lot of variables right here. We just want to make sure that our units are going to work out right, so let's do this calculation at least one time. Here we have the mass flow rate was equal to the velocity at the inlet. That's 200 meters per second times area. Area at the inlet was 0.4 meters squared. Then we had times P1 and the molar mass. So P1 was 80 kilopascal. And for a kilopascal, that's kilonewtons per meter squared. Then we had the molar mass here was 28.97. I'm going to have to squeeze it in here. Kilograms per kilomole. On the bottom, we had the universal gas constant, 8.314. Kilojoule per, I had the units written wrong right here. This is not kilogram Kelvin. This is kilomole Kelvin. And we multiply that by T1, where T1 in Kelvin was 283. Alright, so let's first of all check on the units before we try to cancel anything else out. Here we have meters squared, those two things will cancel out. Here we have Kelvin, that'll cancel out. Here we have kilomole, those two things cancel out nicely. And then what are we left with? We have kilonewtons on the top here. We have kilograms. We have a meter, right? And then we have kilojoules on the bottom here. Our mass flow rate should come out in units of mass per unit time, so kilograms per second. So this second should stay, this kilogram should stay. And then we have a kilonewton times a meter. That's the same thing as a kilojoule. So we can go ahead and cancel the kilojoule with the kilonewton times meter. That means our units are kilograms per second, and we don't have to do any other unit conversions. So we can just punch this into the calculator to get our mass flow rate. So we'll say that the mass flow rate is equal to 200 times 0.4 times 80 times 28.97, then divided by 8.314 divided by 283. So we get 78.8 kilograms per second. That is our mass flow rate through the device. And it's a constant rate of mass flow rate through the device according to the mass balance equation. Alright, so we've used our first equation, that was the mass balance, and then the next thing we need to do, we're looking for T2, and we're just going to try the energy balance equation, see how that can help us. So let's write the energy balance equation next. For the energy balance, we want to start off with the correct form, the single stream form, because we have one inlet and one exit. So first of all, we just write our equation. Q minus W is equal to delta H plus delta KE plus delta PE. And then we apply the conditions that we said are for a diffuser. So we said there's no change in potential energy, it's negligible, no work, and also no heat transfer. So our energy balance gives us one equation, delta H is equal to negative delta KE. So we could write this as something like H2 minus H1, that's delta H. Negative delta KE would be KE1 minus KE2. So we're solving this problem. We still don't see temperature in here anywhere. That's okay. We'll get there. What we want to do, we have that the kinetic energy at the exit is roughly 0. That was one of the given information we found in our properties. So kinetic energy at the inlet, that is 1/2 V1 squared. And then here we have this delta H. So delta H is always dependent on what type of substance we have in the problem. So in this case we have an idle gas. So whenever we have an idle gas, we don't actually calculate delta H, or in chapter 3 we didn't calculate delta U by going to the properties tables, looking up U at the given pressure, temperature, all of those things. Right? We have an equation that describes delta U and delta H for an idle gas. So do you remember that equation? You might take a look back in your notes and see if you can find the equation for delta H of an idle gas. If you remember in chapter 3, whenever we had delta U for an idle gas, we wrote that as C sub V delta T. It's actually very similar for delta H of an idle gas. For delta H of an idle gas, instead of C sub V, we use C sub P. So we write delta H for an idle gas as C sub P delta T. And then KE1, we can write this as 1/2 V1 squared. So this is one key thing we have to remember. For an idle gas, we calculate delta H as C sub P delta T. And then we just have our governing equation now. Turns out this equation has T2 in it, so we can solve this equation for T2. If we solve this equation for T2, here I need to divide by C sub P. So I end up having 1 over 2C sub P times V1 squared, or if you prefer I can write it as just V1 squared divided by 2C sub P, and then I need to add T1 over there. So this is our equation. We know V1, we know T1, we need to look up C sub P. Okay, and C sub P, technically, remember we talked about C sub P should be an average specific heat between temperature T1 and temperature T2. But this is one of those cases where we don't know the value of T2, so we can't actually take an average between T1 and T2. So in this case, I said that it's just acceptable to go ahead and use C sub P at T1, and that's all we need to do for the homework. On the exam, you would just use C sub P at 300 Kelvin. So let's look up C sub P at our temperature T sub 1. We're going to go to the tables, and the specific heat tables are at the very end of the properties packet. Here is the C sub P column for air, and then our temperature is 283. So we know C sub P at 250, we know C sub P at 300. We can interpolate to get our C sub P at 283. So doing the interpolation real quick, our C sub P value we're going to interpolate here between our known table values, 250, our value is 283, and then the other table value was 300. Then at 250 we have 1.003, at 300 1.005. So filling that in, we have 1.003, 1.005. Our C sub P value that we're using is here going to be 1.0043. And units on C sub P, kilojoule per kilogram times Kelvin. So there's our specific heat value we're going to plug in here. Now everything is known in this equation. We should be able to solve for T2. So for T2, let's go ahead and check the units. Anytime you have velocity in an equation, you need to check the units. So we have velocity in this equation. Let's make sure we have our units correct. So velocity at the inlet was 200 meters per second. Then we're supposed to square that. And then we divide it by 2 times our C sub P value, 1.0043 kilojoule per kilogram times Kelvin. So that's V1 squared over 2 C sub P plus T1. T1 was 283. So if we want our temperature, it's going to come out in Kelvin. That's the good unit. This one is in Kelvin, but here this is meters squared per second squared, and then we have kilojoule per kilogram. This Kelvin is the one that's going to come up to the top to give us our temperature in Kelvin. So what is the conversion between meters squared per second squared and kilojoule per kilogram? So let's look at, for a second, a kilojoule per kilogram. If we break this down into more base units, a kilojoule is a kilonewton times a meter. And then we have here per kilogram. Then if we break up a kilonewton, we have a kilo. A newton is a kilogram times meter per second squared. So here the kilograms will cancel out, and it looks like a kilojoule per kilogram is a kilometer squared per second squared. So we have 1 meter squared per second squared here. We need to convert kilojoule per kilogram to meter squared per second squared. That means that here we have a kilojoule per kilogram is 1,000 meters squared per second squared. So we end up dividing that by 1,000 to make sure that the units cancel out right. So now that gets rid of this meter squared per second squared, get rid of kilojoule per kilogram, and Kelvin is what we have left. So all of this to say that our temperature, T2 is equal to, we had 200 squared. Then we multiply by the conversion factor, 1 over 1,000. And then we also divide by 2 and our C sub P value. Then we add plus 283, that was T1. So T2 ends up being 302.9 Kelvin. Or we can just round it off as 303 Kelvin. So what we did, we used both the mass balance and the energy balance to analyze a diffuser. So we used the steady flow equations, and we used the single stream, which is one inlet and one exit. If we look at the properties, right? If we look at the properties, we know that the velocity in the diffuser is supposed to decrease, which it told us that it did. It said V1 was 200 meters per second, V2 was a very small number. And then we didn't actually even look at the pressure P2. We don't know really what the pressure P2 looks like. So we can't say whether or not the pressure increased without doing a little bit more of a calculation. Alright, this pretty much wraps up our diffuser problem.